All right, welcome back, guys. So let's continue on with our discussion here. So, like I said, basics background of what we're talking about, the whole partial dependency and transitive dependencies are going to be the foundation of our initial normalization from unnormalized through first and second normal form into third normal form. Okay, remember, third normal form is the normalization level that your group project will need to be for the first submission and then for the final submission as well. Okay, you don't have to go to the higher forms, to fourth or fifth or Boy's Cod or any of that. We will talk about those. We won't talk about those today. That's going to be beyond the scope of today's lecture. But you don't have to go into those higher levels. So at the end of today, you will basically have about everything that you'll need to at least get to where you need to be for your group project for the first submission. What I'll do tomorrow is I will go through a normalization process with some example data with you guys. So that's what we'll do tomorrow morning. Okay. All right. So let's talk about the process of normalization. Okay. So it's a formal technique. So basically, again, we want to have a systematic approach. We want to take our data and we want to utilize a systematic approach to identify functional dependencies, and we want to be able to take those functional dependencies to create secondary relations based upon our primary relation, based upon the initial set of data. Okay. All right. So let's talk about how identifying those functional dependencies. So we want to identify all functional dependencies. We want to basically take a look at all the columns, and we want to have a complete set of functional dependencies where every column in our table is either on the right side or the left side of some functional dependency somewhere. Okay, doesn't mean they're all going to be on the left side, doesn't mean they're all going to show up on the right side, but they're all going to show up somewhere in our set of functional dependencies. Okay, so for our example, staff branch, right, we could identify the functional dependencies as so. Right, now these are some examples. Okay, notice that even with just these first two bullets, excuse me, with just these first two bullets, we've already gotten all of the columns covered. They're all on some left or right hand side of a functional dependency. Actually, technically, even this first one here shows a functional dependency that consists of all columns in our relation. What that should tell you, by the way, is if you have one function about, we have a column or set of columns over here on the left side and all the other columns in the relation on the right side. Whoa, what does that look like to you? What do you think? Is my microphone working? Oh. You guys are not hearing the sound? Let me try turning this. Can you hear me now? Can anybody hear me now? Okay, hmm, hmm. How about, does it work now? I wonder if it's a call thing. Okay. Now, is it working now? Is it working? Okay, let me try to leave and rejoin. Okay, is it better now? Is it any better? Okay. All right. So let's see. Let's go back then. Let's go back a couple of slides. Because what we're talking about here is we're talking about trying to take our transitive and partial dependencies to begin the process of normalization. The main point of this is that what we want to do is we want to execute a series of steps. We want to have a series of steps of formal process of systematic approach. Right, to get from an unnormalized data set into a, I've heard is that the third, what? Okay. For your first and final submission for your group project. Okay, you're not required to be on third normal form. You can go, you can, in fact, basis, once you get to third normal form, you really won't be able to go any higher than that, but you're not required to go to fourth or Boyce Cod or fifth or any of that. All right, but third normal form. So at the end of this lecture, you will have all the slides that you need. We will have gone over all the slides for you to be able to do your group project. Tomorrow, we will do an example using example data of how to take existing data and from um, um, uh, the first thing you'll need to do is identify functional dependencies. Okay. Now you want to make sure that you have a full set of functional dependencies, and so what you will need to do is you will need to have every column show up somewhere in a functional dependency, whether it be on the left or the right side of a functional dependency. Okay. Once you have all columns covered, that doesn't mean you have all the functional dependencies identified But so now notice that even this first bullet point here, the staff number determines all the other columns. All columns are covered just in there. But we do not have a full set of functional dependencies just off of this first bullet point, because there are other dependencies that also exist. Okay, but what the question was, what I was asking when you guys said that there was a bunch of audio problems, is that when you have this a single column or a set of columns on the left side determines all of the other columns on the right side, what do you think that means? What do you think that indicates? Ah, I didn't share the screen. You're right. I've been sitting here clicking through the slides, talking. Okay, let's try that again. Okay. When you have the staff number, like in this example, staff number, right, determines all of the other columns. If you had a column or set of columns over here on the left side, determines all of the other columns on the right side. What do you think that means? Right. Well, yes. Furkan, it's you don't need the word supreme, but yeah, that is basically what it means. Is that the staff number would be the primary key of the staff branch relation. So if we go back and look at the staff branch relation, notice the staff number determines all the other columns. So staff number is the primary key of this relation. Okay, good. We do have a transitive dependency here. Right. Branch number also determines branch address. Okay. We also have this branch address determines branch number, but we talked about this with the staff example that this may not be a true dual dependency, that this may not be true for all time. Okay. And we have some combination dependencies like branch number and position determine salary. But that's only probably true in our example data, isn't it? Now, there are lots of functional dependencies that we could come up with, right? We could have branch number and position determines name, I think, right? Branch number and position determines name. Branch number and position determines name, branch number, position, right? We could have branch number and name determines position. We could also have it that way. Right? So there are all lots of possible functional dependencies we could come up with. The main ones we're going to be focused on for this example are these first two. Okay. We could also do some examples. We could do an example. What I would like to do is cover up some of these on the next ones, but yeah, well, I don't think it's going to be possible. Okay. Actually, you know what? It probably will be, actually. One second. I'm going to do something behind the scenes. Oh, that's not it. Do one thing. Oh, hold on. Sorry, I'm going to be doing some magic over here. All right. Okay. All right. Okay, so here we have a sample relation, all right, where you have column A, B, C, D, and E. Okay, what are some examples of functional dependencies that you can? What do you think? What are some example functional dependencies that you see where one column, the value in one column determines a value in another column? Okay. Mustafa says A determines C, huh? Yeah, good. Right, because if an A value is here, a Z or a Z value is here. If an E value is here, an R value is here. Yeah, good. So A, Z, E, R, A, Z, E, R. Good. Okay, yeah. That's one. All right. Any others? Does it go the other way? Does C determine A? Does C determine A? Right, yeah. For this particular dependency, it does work both ways. So we could call that functional dependency 2. So far we have 2 of our 5 columns, but we're still missing 3 columns. We don't have 3 of our columns involved in a functional dependency, do we? What's another one then? Is this harder than it looks? Murat says that B determines D. Let's take a look. A B value here gives me a W value here. Does a B value here give me a W value here? Yeah, okay. A D value here gives me a W here. A D value here gives me a W here. Okay, so far so good. An F value here gives me an S here. An F value here gives me an S here. Well, sure does look like that sure does look like that's a functional dependency. Yeah. Okay. Yeah, so B determines D. Does that work in reverse? Does the value in D determine the value in B? Right, no, because here we have a W in D that results in a B in B, but a W here results in a D over here. Okay, so that, nope, D determines B, not one of our functional dependencies. So we've got to figure out some way to get E involved, don't we? Because we only have E left. All right. Which I can tell you something is going to determine E. Well, let's see. Does that work? E determines B. Let's see. Q gives me a B, but Q gives me a D. So that's not right. E determines Q gives me a W. Q gives me a W. Huh, okay, that's good. P gives me a W. Oh, okay, but P doesn't show up again. That's fine. T gives me a W. Oh, T gives me an S. Nope, E doesn't determine D. Okay, so I've given you a hint in that it's something is going to determine E. Okay, so I'm giving you a small hint there. Well, let's see. Is it A? A gives me a Q. A gives me a T. Okay, can't be that. B gives me a Q. B gives me a P. Nope, can't be that. Z gives me a Q. R gives me a, sorry, Z gives me a Q. Z gives me a T. Nope, can't be that. W gives me a Q. W gives me a P. Nope. So it can't be a single column, can it? One single column on the left does not determine what E is. It must be the combination of two columns. Okay. So what do you think it could be? Well, what about the combination of A and B together? A, B? Yeah, Metahan, I can tell you one thing just from experience is that if you see that A and C are kind of this doubly kind of both ways, A determines C and C determines A, then the combination of those two will be the same as anything else. Will be combination of those two together would be the same as A. All right, so B, C, right, where C and A, because of this, A determines C, C determines A and C become interchangeable. Okay, so the combination of B and C, as Murat is suggesting, B, Z, Q, B, R, P, D, Z, T, D, R, Q, F, Z, T, F, R, T. Yeah, you know what? Because these are unique, then yeah, that's the only thing that could combine together to determine E. Right? And it could be either Murdoch E determines E, or A, B determines E. Either. No, there. It did some funky formatting thing. Either one of those would be true for this set. Notice D cannot be involved in this one because B and W together, sorry, not B, A. A and W together give me a value here, but A and W here give me a different value on this row. Okay, so what we would say is A and B together give me this functional density 4. Like I said, this could have also been the combination of B and C together determine E. Either one of those is possible, right? And that's because this kind of double functional dependency kind of relationship that column A and column C have with each other. Okay. So we are seeing these are our 4 functional dependencies we're going to work with on this example. We would write them out like this. So now notice, question. One second. Okay. So now notice that here, A, B, C, and D all show up on either the left hand or the right hand side of a functional dependency here. Right. So now we need to identify what is our primary key. Which do you think is our primary key? So I'm going to say that's the next thing we're going to talk about here. Okay. Well, Furkan, does B determine all of the other columns on its own? Remember, what we're looking for is we're looking for a column or a set of columns that is the determinant, that is the left side for all the other columns. Right, I'm going to side with Mustafa here on this one, that A and B together seem to be our primary key, right? Because A and B determine E, A determines C, and B determines D, so therefore A and B must also determine C and D, right? That's our transitive dependency, or partial, right, rather partial dependency we talked about earlier, okay? So the way we could write this, let me go ahead and edit this. Not what I meant to do. Okay. We could say it like this because we know that A and B determines E. We also know that C is determined by A alone. So this would be what we call a partial dependency. And then D is determined by B alone. So it is also a partial dependency. Okay. And since we have some set of columns on the left that determines all of the other columns on the right, we now know that this is our best chance at a primary key, or one of. Let's say this. Let's not call it our primary key for just yet. We'll call it our candidate key. Okay, we'll call it a candidate key. Okay. So we want to identify the primary key using our functional dependencies. Okay. So we want to identify first all possible candidate keys. Okay. So here, what we're trying to do is we're trying to say, okay, what is an attribute or group of attributes that uniquely identifies all the others? Okay. For the staff branch relation, the only if we look at the functional dependencies there, the only column or group of columns that uniquely identifies all the others is the staff number. That's the only one we have that does this. Okay, so this would have to be the only candidate key, and therefore the primary key for this. Okay. All right. If we go, however, with our example data, all right. All right. If we look back at our examples here, we have this A, B determines E. And one thing I wanted to go ahead and I also wanted to go ahead and say here was we had said this too. This was also possible. Okay. That BC determines E was also a possible functional dependency that could exist. Okay. All right, so A and B together, B and C together. All right. So we could say that A and B, right, is a candidate key. B and C is a candidate key. We could choose either one of those, either the A-B combination or the B-C combination to identify it as the primary key. All right. So here we just choose A and B. We like A and B, I guess, right? Okay. All right. So that's identifying the primary key, which basically is once you've done that, once you have taken a data set and given it a primary key, that's the first normal form. Okay, that's what we're going to call the first normal form. All right. So here, let's say outside of this, we have what we call an unnormalized form. In fact, I can draw that over here. Okay. Outside, let's say we have the unnormalized form of our database. Okay. And what an unnormalized form, there's all kinds of like definitions for what unnormalized is. Basically, it's just a set of data. It could be in an Excel spreadsheet format. There could be duplicate data. There could be merged cells. There's all kinds of things that an unnormalized set could look like. Okay. The first normal form is simply every, well, I think it's actually defined here. So, okay. Let's say we get our data sources, we create an unnormalized form. We move to first normal form by removing repeating groups and defining a primary key. When we remove partial dependencies, we get the second normal form. When we remove transitive dependencies, we get the third normal form. Okay. We'll talk about how to do that here. Okay. So basically, to get an unnormalized form data set, database, we just take the data from the information and create it into a table format. It could be an Excel spreadsheet. It could be a comma separated values. It's lots of different formats are possible. Okay. You could have repeating groups. All right. So tomorrow, like I said, tomorrow I will show you an example that contains this. Okay. The first normal form is we have a relation now where each row and column contains one and only one value. No repeating groups. Each cell contains a value. Okay. Now the way that we create that first normal form is first we need to find an attribute or group of attributes to act as the primary key. All right, so we need to nominate a primary key, and we basically need to remove the repeating groups. Right. So we need to take appropriate data, flatten it out, index. Like you mean the ID column, like the staff number, branch number? Is that what you mean, Mustafa? Well, those columns were named that, and a lot of the in a lot of the situations, that column was created. Oh, first row, second. Well, because, well, let's take a look back at what cell was it? Here. Okay, we'll take this B005 here. Okay, that's going to become the key of the branch table. The branch number is going to be the key of the branch table, but it's both the first row here and the sixth row here. All right, but it's only the first row here. And the point is, what we're trying to do is we're going to try to take like these two columns here. We're going to try to make them their own relation over here so that we avoid duplicated data. We minimize space. All right. Well, that's a good question, though. Let's see. Okay. And you'll see what I mean by this whole repeating groups is one of the nice things about Excel is we can like merge cells together. Excel and Google Sheets and stuff like that. We can merge cells together, but it also means that for a database, it doesn't exactly work very well to have merged cells. All right. So what we're going to do is we're going to copy data into the empty columns or rows. Yeah, or by placing the repeated data with a copy of the original key into a separate relation. So we may even in the first normal form be creating a separate table, separate relation. Not common, but it does happen. Okay. But basically, what we get to with a first normal form is we get a complete grid. There are no merged cells. There's no repeating rows. There's no repeating columns. It's one Excel spreadsheet with no merged cells and one column or set of columns to represent the primary key of the whole thing. Okay. So once we have that first normal form, we can move to second normal form. Okay. So this is based on the idea of full functional dependency. So if you remember, full functional dependency is where our column on the right-hand side is dependent on the column on the left-hand side, but not on any subset. Okay. So B is dependent on A, but not on a subset of A. So for example, if we go back to, let's see, what slide was it? Was it here? Here. Okay. Here, C is dependent on A and B. That's true. If we go back and we look back at this grid here, is C dependent on the combination of A and B? Yes. Well, really, it's just because C is dependent on A alone. We don't really need B involved in this. So C is dependent on A and B is a partial dependency. That is not a full functional dependency. So we'd like to get rid of that. We would like to focus on this rather than this. Okay. Let's go. Okay. So what we want to do is that if a partial dependency exists on the primary key, remove that and create a new relation along with a copy. Okay. So the way we might do that here, let's see, what slide was it? No, not that far back. Okay, so this A and C, so C is dependent on A and B, but C is really just dependent on A. So what we would do, we would say, okay, we really don't need C to be in this relation. What we can do is we can take this. I'm going to crop this out and show you. This isn't going to work, is it? Ah, it is. Okay. All right. One more. We don't need that. And we don't need that. It's a little crude. It's a little not well done, but I think you get the idea. I hope that what we could do is we could create this relation on its own, this AC relation, with just these two rows, and we wouldn't even need this column C in this relation anymore. Okay. You guys understand what I'm saying here on this? Is that because this partial dependency exists right here, we don't need C in this column. I mean, we don't need C in this table. We could create our own relation over here, this AC combination, where A determines C, keep A over here in this table, and get rid of the C column. So we've gotten rid of 6 cells right here that we didn't need. Okay. Let me clean this up just a little bit. Okay. All right. And what I'll do is I'll say I'm going to put a little rectangle here to show that that's not even there anymore. Let's see. Oh, where are you? I want to like, no, there it is. I want it transparent, more transparent. Okay. All right. And we can do this with B and D as well, right? Where we have the B columns here. Okay. And what I'll do for this one is I'll do this a little bit different because it's going to be a little bit more hard. B, D, and 3 rows. B, D, B. B, W, D, W, and F, S. Okay. Okay, so now we have these two columns here removed from our original relation, right? And made into their own over here. So look, just from this, think about how many cells we've now saved, how much space we've saved. Over here we had how many cells? We had 1, 2, 3, 4, 5, 6 by 5 is 30 cells. Okay, we got rid of 12 and replaced it with 10, right? Because we created new tables. Okay. We created new tables over here to store these values. Okay. It may not seem like a lot of savings. I mean, come on, we got rid of 12 cells and we replaced it with 10. It seems kind of, you know, it seems like it's not a lot, right? Not a lot of savings. But when we're talking about millions of rows, millions of cells that could be stored over here, plus the data redundancy and the update anomalies we no longer have to deal with, it can get to be pretty big of a deal. All right. All right. So again, we identify the primary key. If there are partial dependencies of the primary key, we get rid of them by making a new relation, a new table like I showed you on that previous slide, on that other slide. Okay. All right. The third normal form, going from the second to the third, is we're getting rid of transitive dependencies. So now it's kind of similar in that one determines another, B determines C, and the solution is the same as the second normal form in the sense that we are identifying a primary key. We are, if the transitive dependency exists, we're getting rid of that transitive dependency by creating another table, another relation, right, with a copy of that primary key. So if we go back to our example here, there are no transitive dependencies here, right? There's nothing where something determines something else and then that thing determines something. So it's not like A determines C and C determines something else, right? We do have a couple of partial dependencies here, but we don't have any transitive dependencies. But you know an example where we did have a transitive dependency? Right here. This was a transitive dependency. Staff number determines branch number determines branch address. So what we don't want to do is we don't want to have this in the main table. So what do? We take these columns here. We create a new table with just the non-repeating, right? So just B005, just B007, just B003, one time each. This that's on the left side of that functional dependency becomes the key of that new relation. These values become the values over here, and we only keep this as a foreign key over here. Okay. All right, so first normal form, we have a grid and a primary key. Second normal form, there are no partial dependencies. The only things that are dependent on the primary key are only dependent on the primary key and no subset. Okay. Third normal form, no transitive dependencies exist. If something is dependent on something other than the primary key, we remove it and put it in its own relation. Okay, so that's how we get from unnormalized all the way up to third normal form. All right. If there are any questions, we can do that. Otherwise, we will end there for today. Okay. Otherwise, we will end there for today. And tomorrow we will go through an example where I'll have an unnormalized data set to start with, and I will move that data set all the way from unnormalized through to the third normal form. Okay. Does anyone have any questions before we end? Or comments? Oh, I do want to say something about Mustafa. You did ask about this index. Like, I'm assuming you mean like the first column. The first column might not always be the primary key. In fact, I'll probably do that tomorrow. What I'll do tomorrow for an example set of data is I'll make sure that the first column is not a good primary key. All right. Anyone? Okay. All right. Well, we'll end there for today, and I will see you guys bright and early tomorrow morning. Oh, we can. It's just sometimes that's adding more data. And if we have some column that already makes sense as a primary key, for example, here at the university, your student number was assigned to you, right? But that was what the university did to make the primary key the easiest thing for the student table. You can, but what if the data was consisting of not only you as a student but also course information? Should we have a primary key, that represents? Should we create a new number that represents Mustafa taking 204, Mustafa taking 102, Mustafa taking that? That wouldn't make much sense. I think you'll see tomorrow when we do the example data, because all the different tables that it might come from, it wouldn't make much sense to create an own primary key when the data is a mixture of a bunch of different categories. When the columns are from a bunch of different categories. I think that may help you understand that better. All right. Sorry, I can't answer it more clearly today. I think an example will be much more helpful for you. But that is a very good question, because it makes sense. You see it in here. You see it with your TJ number, with your university student ID, with a banking account number. They just give you a new number. Yeah, and so it does make sense that seems to be a solution. All right. If no other questions, then we will see each other tomorrow morning, and we'll talk then. All right. Have a good afternoon.